are there any questions before we get started? If not, then let's get back to studying the asymptotic extension of integral. Okay, we say that if we have an integral of this form, dt ft g lambda t, and we need to integrate this function, and g lambda t has a property that it behaves like a highly oscillatory function when lambda becomes infinity. When lambda is very large, this thing just has to vary a little bit, and then the phase of g lambda or t will be very rapidly changing, and hence this integral can be rapidly oscillating. So what you do then is to find the stationary point of the function in the exponent. If this is the stationary point, then we have this property that h of t will be slowly varying around this point. And then if you look at g of lambda, then it will be just plotting either the real part or the imaginary part. It will be slowly varying and then rapidly varying after that. It slows down near the stationary phase point. This is called the stationary phase point. And then we can hence approximate this integral. I has been equal to f of t naught minus infinity to infinity dt. G of lambda t. And if we can perform this integration in closed form, we find an asymptotic approximation to this integral I. Okay, this is the essence of the stationary phase point method. And let's try an example where my I is one of the Sommerfeld integrals that we have studied before. Okay, we found that our Sommerfeld integral can be written in this manner: e to the I k z z plus r1 2 t and e to the I k z z plus 2d1. Okay, this is for the case of a point source, a vertical electric dipole located on a half space where z equals minus d1. And this might be region 1, and this might be region 2, and this is a vertical electric dipole. Okay, and this point is at z equal to 0. We know how to solve for this solution. Let's call this K1C to be more precise. Okay? And this Sommerfeld integral can be evaluated numerically. And when you evaluate numerically, when rho and z are large, the integrand can potentially be very rapidly varying. Okay? So let's look at one of the two terms. You can apply the stationary phase method to either the first term or the second term. Let's just look at the reflected term, which is the second term. It will be something of this one. I'm just ignoring the constant up front. The reflected wave term looks something like this. And then it has this exponent e to the I k1 z z plus 2d1. Okay? And then plus the reflection coefficient. And this reflection coefficient is rather complicated. It will be something like mu 2 k1z minus mu 1 k2z, and then mu 2 k1z plus mu 1 k2z. And in general, kiz is equal to square root of ki squared minus k rho squared. Okay? And there's no way you can evaluate this integral in closed form, but we can use the method of stationary phase to find the approximate value of this integral. Okay, let's see how we do that. We know that H01 K rho has an asymptotic value of this form. If you look up the asymptotic expansion of this integral, when K rho becomes very large, not K rho becomes very large, and rho becomes very large, K rho fixed. If you fix K rho and make rho very large, meaning that you're making your observation point very far away from the source point, or you will find that the Henkel function can be approximated as such. And then it's going to be a rapidly varying function because rho is large. You just have to change K rho a little bit. The phase of H1 will change rapidly. Similarly, this term has the same property that K1z has to be something of this form. So when z is very large, when you're at certain point out here, say out here, over here, your observation point is out here, very far away, both z and rho are large, K rho has to change a little bit, K1z will change by a little bit, but because of the largeness of this value, the phase of this term will change rapidly. Okay, so we have two functions whose phases could be rapidly varying, and let's apply the method of stationary phase. And first, let's try to identify what h of t is in this integrand. So let's group together the rapidly varying phase function. So if you group together the rapidly varying phase function, the term coming from there is that term over there. Another term coming from the K1z is this term over here. Okay? So this can be thought of as something like I lambda h of K rho. Our variable is not t here, our variable is K rho. We can lump this together and think of this as that. And what we need to do is actually to find the value of K rho for which the derivative of this is equal to 0. We need to find the stationary phase point, which is this equation over here. So we need to differentiate. Okay, we can think of my lambda h K rho as being equal to K rho plus K1z z plus 2d1. So I'd like to find out the value of K rho that will make this stationary. So I differentiate it once. And the first term will just give me rho. The second term I have to differentiate K1z with respect to rho. It's quite easy to differentiate K1z with respect to rho, or K rho, sorry. It will be the differentiation of K1 minus K rho squared with respect to K rho. And by differentiation with the chain rule, this gives you minus K rho over K1 squared minus K rho squared. You just apply the chain rule, you get this, which is minus K rho over Kz. So the second term gives you K rho over K1z, okay, K1z, z plus 2d1. And we'd like to set this to 0. Okay, we'd like to set this to 0, but let me tell you a simple trick to make the solution of the equation simple, which is by a simple change of variable. So I let k rho is equal to k1 sine alpha, k1z is k1 cosine of alpha. Okay? I change my variable to alpha. Then that equation can be written as rho minus k rho is k1 sine alpha. Okay? And then denominator is k1z becomes cosine alpha. So this becomes cosine alpha. And then I just have this. Z plus 2d1 equal to 0. And you can probably see that the solution to this equation is that if I pick sine alpha to be equal to, actually I can use the coordinate system to help you, d plus 2d1, and you can think of this as being theta. Okay, this if your observation angle is here, this is theta. And then if I write a similar one in the cylindrical coordinate system, then this is equal to alpha. I think that's what I have here. Okay. And if I pick sine alpha is equal to sine theta, then I find that sine theta is just equal to, let me see. I can rewrite this as such, right? And rewrite this as rho over z plus 2d1 minus 10 alpha is equal to 0. But rho over this thing is just 10 theta, right? Tangent theta minus tangent alpha is equal to 0. So very clearly, this is a solution. If I take beta equals to alpha, I have the solution to this problem. So the stationary phase point, of course you can go through a more longer algebra, but this is just a shortcut. So k rho is stationary when k rho equals k rho s, when k rho equal to just when alpha equals theta. So this is a stationary phase point. This is the stationary phase point in the complex k rho frame. And that is the value that will make the derivative of this equal to 0. Okay? And this is what I have by solving this equation. The next thing that I need to do then is to do the argument that since this integrand will be highly oscillatory when rho and z are very large, most of the contribution to this integrand will come from points near the stationary phase point. Hence, I can pull out the slowly varying term, pull out a slowly varying term, and then leave whatever that can be integrated in closed form back into the integrand. So I do this trick by pulling out the slowly varying term. I'm saying that if I put out a k rho square here, making this into a k rho square times k rho, I'm saying that k rho square does not have a phase function associated with it. Plus this one does not have a phase function associated with it. I'm going to say IR is approximately equal to k rho square times R1 to Tm evaluated at k rho equal to k rho s. Okay? And take the slowly varying term out and put them outside. And then leaving behind what I think could be integrated in closed form. I deliberately leave behind a k row here. I deliberately leave behind a k1z here. And then I deliberately leave the other terms behind. And then I have this left-hand side. Can you recognize what this integral is? And if I were to ask you to give me the closed form expression for that, what would that be?
Scalar Green's
Right?
Scalar Green's function.
Scalar Green's function, correct. Tell me what more precisely.
Sum of your
What?
sum of your identity.
Is the sum of your identity, some of your identity that we have learned. Look exactly like that, right? We have learned the fact that if you have something like this, this is equal to something like that. Okay, very good. This is precisely the sum of your identity. This thing evaluates to that. And hence this thing must be evaluating to something that looks like that if you know how to identify what this term is, what k1z is, and so on. I'm saying that by inspection, so I can put k rho squares here, and then R12Tm evaluated at k rho s. Okay, but what is this? This is just equal to 2 over I. And then, should I change the kr here into k1? Because all I have is k1z, right? So I should change, so I would have k1z equal to k1 squared. The medium has a wave number of k1, so it should be k1. And then the r, and the r I cannot use back the same r over here. The r in this equation that I had previously, this r over here is square root of rho squared plus z squared. So I should try some sort of a new r, which I call ri. Okay. If this equation dictates that r should be that, what should ri be? Simple IQ test. Right? What should ri be? Yes?
Z plus 2b1.
Not just that, something more than that. Simple IQ test, okay? If r in this equation is equal to that, and if I want to write this in terms of this, what should ri be?
Squared, rho squared plus, and then it's going to be z.
Okay, very good. Ri should be simple IQ test, rho squared plus z plus 2d1 squared, right? Just identify this term with that. This is always positive. Okay, we're in the upper half space. And then this should be rho, and this is my Ri. So this is the asymptotic approximation for that very complicated looking Sommerfeld integral. So what is the meaning of this? This apparently is a spherical wave. It's a spherical wave, but where is the spherical wave emerging from? Well, if you think about it properly, if I have a VEV, and this is located at z equal to 0, and there is a half space at z equals to minus d1, and what is Ri? Okay, Ri is actually this distance. This distance here is d1. Hence, this distance here is 2d1 in total. And then if you are at an observation point over here, which is z above the source point, okay, but at the distance rho, this distance here is rho in the radial direction, then this distance, as you can see, this distance here is what I call Ri. Okay, this distance here is what I call Ri. Ri, if you look at this, and if you know Pythagoras theorem, this is just equal to, this distance is c plus 2d1 and so this is a spherical wave that is emerging from this image point. Okay, it is a spherical wave that emerges from the image point, expanding and then reaching the observation point. Okay? But this reflected waveform is modulated by this coefficient. This coefficient here is the reflection coefficient of a wave that is incident at this angle. Okay, I can look at this angle k rho s. K rho s is given by sine theta, and that theta is actually this theta. Okay, if I look at what this theta is, that theta I have drawn there is actually precisely this theta. Okay, let me call it, to be more precise, theta I. Okay, and this is actually my theta I, the angle of the image point. So I can actually call this theta I if I want to, theta I, to be more precise. And then this would be the reflection coefficient, the Fresnel reflection coefficient of a wave coming in at an angle theta I. This is also theta I. Okay? So what does this tell you? This tells you that this is the Fresnel reflection coefficient evaluated with k rho s is to the k1 sine theta I. Kzs is k1 cosine of theta I. Okay? And if you go about writing the Fresnel reflection coefficient again is mu 2 k 1z minus mu 1 k 2z over mu 2 k1z plus mu 1 k2z. And if you look at this evaluation, this means that this is the Fresnel reflection coefficient for a plane wave coming in at this angle. Okay, so this is actually ray theory, ray physics. What ray physics say is that you feel far away can be approximated by a spherical wave whose ray seems to be coming from this point, and then the wave is actually a reflection of this wave coming in. It's reflecting via a local Fresnel reflection coefficient. This is ray theory. Yes? It doesn't bend. No, it doesn't bend. No.
It's just an image.
It's just an image. Image doesn't bend. Okay, let me give you another example. If a source point here, say if this is optically more dense, then the ray theory looks something like this, okay? But then to find the image point, you use this angle, theta, to find the image point. This is the image point. This is the source point. This is the observation point. Okay, to find the image point, you don't bend the ray. This ray does bend. This ray that is transmitted does bend. But to find the image point, you don't bend the ray. Okay? So this is actually ray theory. And what we have gotten is to use the stationary phase method to extract ray physics out of a very complicated integral. So this is one thing that you should know. And what is the other thing that you should know? we had an integral that was initially a linear superposition of plane waves. We say that if we have a source point, we do Sommerfeld expansion, and using real identity, we can be written as an expansion of rays of plane waves propagating in all directions. But then this plane wave will be propagating in all directions, and it will be all reflected as an integral or integral summation. But if you're over here, only one plane wave is important. Okay, the method of stationary phase will pick up a special plane wave out of that many plane waves that have been transmitted and reflected. Why is that so? Okay, this is also ray physics emerging from wave physics. Say, if I have a Sommerfeld integral or Sommerfeld wave identity, I actually have plane waves propagating in all directions. Okay, I have all these plane waves propagating in all this direction. But the method of stationary phase says that only one ray is important. If you were to put the observation point over here, even though they are all rays zipping past you, okay, only one ray is going to be important that reaches you. And all the other rays are not important. Or all the other plane waves are not important. Why is that so? Because they interfere destructively. And only one ray is going to, only one plane wave is going to interfere constructively. Okay? So this is a rather amazing thing, but you can kind of see it also from this picture. I have a plane wave. The plane wave can be described by this picture over here. Constant phase front of this plane wave, right? It looks something like this. Okay? But it seems to me that this plane wave is being felt by this guy over here. If this guy is over there, he's going to send some of this plane wave reaching him. But why is it that this plane wave does not affect this guy? Only this plane wave that is propagating in this direction is affecting him. Why is that so? This is the consequence of constructive and destructive interference. Let's see how we can see this. So if I have a plane wave, and if I have a second plane wave that is very close to this one. Okay, if I draw maybe I shouldn't draw it, but if I draw the constant phase front, it's going to look something like this. Okay? Something like this. I don't know if you can see from this picture, that is only when these two rays are close to each other that they constructively interfere. But look at here, if they're far away, their phase start to diverge. These are constant phase front. So these two plane waves constructively interfere only in the direction close to the k vector. Away from the k vector, they destructively interfere. So for this reason, if you have a bunch of plane waves propagating to you, only these two plane waves that are very close to each other will constructively interfere here. The other plane wave will destructively interfere at this point due to the losing of phase coherence in other parts of space. So there's actually a very natural beaming effect. This Sommerfeld integral or Sommerfeld wave identity say that these plane waves are all propagating in all directions, but if you're over here, you only feel the effect of this plane wave. Or in other words, this plane wave becomes like a beam now. Okay, instead of spraying itself everywhere, it actually moves its energy mainly in this direction due to constructive interference. So when I say that the Sommerfeld wave identity gives out all these plane waves, okay, I put a lens here, and the lens will only pick up plane wave propagating in this angle. I'm actually invoking ray optics in arguing this picture over here. The ray optics can only be justified by the method of stationary phase. The rays will constructively interfere when they're close to each other. They destructively interfere when they're far away from each other. So you can replace a plane wave picture with ray picture quite confidently. due to the method of stationary phase. So plane waves can be replaced by rays if you have a whole bunch of them. Okay, if you have a whole bunch of plane waves, you can think of them as just rays, because they will only constructively interfere in the direction in which they're propagating. Okay, are there any questions regarding this? Yes?
So when you use the stationary phase method, you make an approximation about the chemical function that is valid for the far field. How about the near field?
Right. This is valid for the far field. I make this approximation assuming that rho is large. I never make anything about k rho. Okay, k rho is fixed. I say somewhere k rho can be fixed, rho can be large. Okay, so if k rho is fixed and rho is large, then I find the stationary phase point to be this one over here. Okay, so I have to be in the far field. I have to be in the far field. In other words, k rho times rho has to be large. Okay, and the whole thing has to be large. Okay, k rho will be equal to k1 sine theta I times rho. This whole thing has to be large before we can do this stationary phase argument. And either the frequency is large or the observation point is large. Actually, it's k1 rho has to be large. Finally, the final analysis boils down to the fact that in order for you to locate this stationary phase point, k1 rho has to be large. Okay? So actually it boils down to what the last parameter is. I did not go into detail in describing that, but the last parameter is actually k1 rho. I have this my h, my lambda h k rho is k rho plus k1 z plus 2d1. Okay? I can actually rewrite this as k1 sine alpha rho plus k1 cos alpha z plus 2d1. Okay? And then I can also rewrite this as k1 r I rho over ri sine alpha plus, I took out the k1, so this should be z plus 2d1 over ri cosine alpha, right? I can rewrite my h of k rho in this manner. I change the variable to alpha instead of rho. And then rho over ri, if you can look at the picture, rho over ri is just sine theta I, right? So sine theta I, sine alpha, and then if you look at this number over here, which is this number over ri, this is ri. Okay, I call ri, but I use a capital letter here. But this is just cosine of theta I, cosine of alpha. Okay, and this is a number of order 1. This is a number of order 1. It's never large. Never larger than 1. But this is a number that is large, that can be made large. How can I make this number large? How can I make lambda large? This is my lambda. How can I make lambda large? There are two ways I can make lambda large.
Shouldn't it be cosine alpha?
The cosine.
Should be cosine? Okay, maybe you're correct. Cosine. Okay. So there are two ways to make this thing large. You can make the frequency high, wavelength short, or you can make the observation point very far away. These are all the important things to make ray optics valid. The observation point has to be far away, or the frequency has to be high, or the wavelength has to be short. And once you have this large parameter, then you can go to this stationary phase point analysis. Okay? And stationary phase point analysis just say constructive interference. Otherwise, it's destructive interference. Okay, so much for this. Yes.
When you combine you also have the incident wave as well. The
Yeah.
incident wave is propagating.
Right. I didn't do that part.
Are we, because the incident and the reflected rays are going to interfere.
They're different. This is just a reflected wave term. If I were to write down the incident wave term, okay, remember what that is?
This will look similar.
It looks similar, but with a difference. Maybe you can go through that. The incident wave is this one. H01, K rho rho, e to the I, K1z, z. Now that you are an expert on the stationary phase method, what is the stationary phase point approximation of this integral? This thing here has changed. So this can be approximated as K rho S squared. Okay, I can take this thing out and evaluate them. And then what is left behind is this integral, K rho over K1z, H01, K rho rho, e to the I, K1z, z. Okay, again, this can be evaluated in closed form using the Sommerfeld integral. And what is it? So this should be equal to K rho S squared 2 over I. What is the Sommerfeld integral? E to the I K1. But that R is going to be different. This R is going to be rho squared plus Z squared. So this gives rise to a different ray optics solution, a ray physics solution. So if you have a source point